Hi there, I am Saniya, and in this video I want to talk about how you can calculate conditional probabilities from a joint probability distribution table. So this will involve using Bayes theorem, which is sort of like this. An example: probability of A given B is equal to probability of B given A multiplied by the probability of A divided by the probability of B. So we're going to talk more about that, but how do you go from a joint probability distribution table to conditional probabilities? So that's what we will talk about. And there are a lot of cute little jokes here and cartoons about how you can use Bayesian inference. So this whole book is full of priors that have to be accepted on faith. It's a religion. And in the public schools, no less. Call a lawyer. As a math atheist, I should be excused from this. So that's a joke as well. And there's another joke. And Jeremy, if you're going upstairs, could you bring these up and put them in the hall closet? If I'm going upstairs? You are going upstairs, weren't you? Not if there are conditions. So they're all about conditions and probabilities. So that's what we will talk about today. I just wanted to kind of loosen it up a bit with a few little jokes. So we're going to consider a joint probability distribution table that has 8 outcomes. Variables A, B, and C. And they're Booleans. So the way I remember it is like boo, liar. So if you look here in the stem of a Boolean, it's like boo. And I like to think of the lien like liar. Like boo, liar, what you say is false. So you can have two values, true and false here. So that's how I sort of remember it. Boolean is like boo, liar, boo, you're a liar, whatever you say is false. So we have these 3 random variables, A, B, and C, and they can be true or false. So, 2 outcomes for A, 2 outcomes for B, 2 outcomes for C, so 8 total outcomes. Here is the joint probability distribution for A, B, and C in this example. So we can see that A is false, B is false, and C is true. And the probability of all of that is 0. Of A being false, B being true, and C being true. All of that is 0.3. The probability that A is true, B is false, and C is true is 0.2 or 20%. The probability that all 3 are true is 20%. The probability that all 3 are false is 30%, 0.3. The probability that A is false, B is true, and C is false is 0. The probability that A is true, B is false, and C is false is 0. And the probability that A is true, B is true, and C is false is 0. So this is the example joint probability distribution for the A, B, and C 3 Boolean random variables. So this is like a Venn diagram for the 3 variables here. So this is like a Venn. And basically, we want to see the distribution of all of them. So we can we live in a world where we can have A being true, B being true, C being true, one of the 3 being true, 2 of the 3 being true, all 3 of them being true, or we can have none of them being true. So I'll just show how to fill up like this Venn diagram basically. So let's see how that can get done. So from this joint probability table, we can basically represent this as follows. So basically here, if A is false and B is false and C is true, then this is 0. So what this is saying is that this is just basically saying C only, which is what this part is. So this part is just the 0 here. The 0, that's what this is saying. This is just C only. And then, if A is false, and B is true, and C is true, this is just the intersection of B and C only. So that is this 0.2 here, basically. Oh, that's this 0.3. Sorry, the 0.3 that is given by the intersection of B and C here. but there's no A that's allowed because A is false. So we only look at this part here, this point 3. That's what this is representing here. Then what this part is that if A is true, B is false, and C is true, this is similarly the intersection between A and C, but it's not including B. So this is the intersection between A and C, which is point 2. So this thing here is basically, this point 2 is just this part here, this point 2. From here, this point 2 is basically A intersect with C, but it does not include B. So this is the part of A and C, but B is not included here. If B was included, it would have been this red part here, which actually is A is true, B is true, and C is true. So this part of the circle falls within all 3 circles. And this is this point 2 here. This point 2 is what this part here is. And similarly, if all 3 are false, that is what's given by this point 3 here actually. This point 3 is basically everything outside of this like figure is point 3. So that's when all 3 of them are false. And similarly, if A is false and B is true and C is false, that's just the probability of B being true, which is just 0. And then the rest are also 0. So if A is true and B is false and C is false, that is just A being only A being true, which is what this orange thing is showing. This orange thing is only A. And lastly, this is just A and B being true but C being false. So that is given by this part here, because this part here, it does not fall within C. So this part right here of 0 is actually this part here. The 0 is the 0 here. So that's sort of how you can take the probability, the joint probability table and represent it in a Venn diagram, and then you can interpret it that way. In this example, we'll also go through 2 example probabilities that are involving this joint probability table. That is, given this joint probability table of 3 random variables, Boolean variables, A, B, and C. So we're going to find the probability that A is true given that C is true. That's what we're going to find as well. That's the first example we will go through. And the second example is the probability that A is true given that B is true. So those are the 2 examples that we will be going through in this video today. So now we're going to talk about Bayes' rule. What is Bayes' rule exactly? So Bayes' rule is trying to find the probability that we observe one random variable, like here, what's the probability that we will observe A, given that another random variable like B has occurred. So what's the probability of A given B? So what it is equal to is it's equal to the probability of B given A multiplied by the probability of A divided by the probability of B, which is also equal to the probability of A and B divided by the probability of B. So in other words, the posterior probability of A being true given that B is true is given by this likelihood, the probability of B being true given that A is true. So whenever you see in probability problems, whenever you see this part here, this part is just saying given. That's what this part is representing, given. So it's always the probability of, this part right before the line, given that this one was observed. So this is the probability of A being true given that B is true. So whatever's on the right is sort of right, and it's sort of what happened first. And then this is the probability of us observing that A, given that this has happened. So this flipped around, you'll see that this and this likelihood, they're flipped around in a way. So this is the probability of B being true, given that A is true. So one way of seeing it is the probability of B being true. Oh, okay, that's probably not the neatest color. So let me just underline it. So this is the probability. Oh, I can't do that either. Okay, let me try it again. Of B being true. So, but here it's flipped around where B is actually true. In this one, B is true. But here it's a probability of B is true, given that A is true. So this one is given that A is true, and this one is a probability that A is true. And you can see that they're like sort of flipped around in a way. So what this is this is the likelihood, and then this is the prior. This is the probability that A is being true. This is the knowledge. And then this is the marginalization, the probability that B is true. So if this confuses you, this over here is just the same thing as this whole expression here. This cute little expression here is just the same thing as the probability of A and B. That's what it is representing. And whenever you're saying the probability of A given B, the denominator, you can sort of think of like this A given B in a way. You can think of it as like this A and then this B. You can think of this part here, this given part, as sort of like, you know, you could think of it as sort of being like becoming the new denominator. So like B gets put on the denominator in a way. You can think of it like the slice is like putting B on the denominator. I looked like I was doing like a Jedi Star Wars move. I love Star Wars, by the way. So this is just the same thing as the probability of A and B divided by the probability of B. So when B happens, what's the probability that A will happen? So if you have like two different outcomes here, if this is like A and this part here is B, so what this is trying to say is given that B has occurred. So now that B happened, what we will see here is that, oh no, that's the wrong color. So so what we'll see here is that B has occurred now. Okay, so B has occurred. So what is the probability that A will occur? So this is the whole like sample space, you know, this is the sample space. You can have A, you can have B, or you can have neither. So I just drew that rectangle as a sample space. So if you now know that B has occurred, what's the probability that A will occur? So what you're going to do is you're going to essentially have in the denominator the probability that B has occurred. Then what you want to see now is that this is our new sample space. We've reduced it from that whole rectangle down to that circle of B. So now from B, what is the probability that A is true? So we want to find this overlap now. So that's how we find A and B being true. That's what we're trying to find, this part here. So ultimately, this part is how now that B is true, that is how A can take place. So if we are now restricted to this blue set here, the only way that A can take place is if A falls in the intersection between A and B here. If it's in the common part between the Venn diagrams, that's the only way that A can happen. So that's why we look at A and B, and that's our numerator. And then we divide it by the probability of B happening in the first place. So that's how Bayes' rule is working. And if you decide, and this is the marginalization, this is shown here as well. You know, probability of B being true, whatever you're conditioning it on. This is a conditional probability. PA given B is a conditional probability. It is a conditional. It's a conditional probability. It's you're conditioning it on the fact out of all this whole sample space that sums up to 1. So this other shaded, no, other part of this rectangle is the part where A and B are not true. A or B are not true. So it's neither A nor B is true. But now if we're just doing the probability of A given B, so we are conditioning our sample space to just B being true. And now we're seeing if B is true, if we're in this blue circle, what is the probability that A will be true? And that's why we look here at the overlap between them. That's also just to keep the color constant. That's also what this purple is trying to do. This purple is just measuring the probability of A and B. Meanwhile, this circle here is only true, for the probability of B. So this is just what Bayes' rule is, and we're just going to use that to better understand the concepts. So also like a very, very fun fact is that Bayes' theorem was invented in 1763 by Thomas Bayes here. So you can see Bayes here. So he was a statistician, English statistician, philosopher, and Presbyterian minister who formulated this. So he did this in 1763, and it seems very complex. I got this from Wikipedia, but this is the inventor of Bayes' theorem. But we're just going to take the general idea because it could be kind of complex in general. If you get into all this math, we're going to use it to just get the general concepts of how you apply Bayes' theorem as well. So I just wanted to give you this fun little history fact. So thus these examples show how Bayes' rule will be used. So if we have the probability that A is true, given that C is true, that's what we're trying to see. This thing represents given that C is true. That is just the probability that A is true and C is true divided by the probability that C is true using Bayes' theorem. So we can look in the denominator and then use that here. But similarly, well, in this case, if we want to find the probability A is true given that B is true, we can similarly just say, okay, B is true. What's the probability that B is true? Then what's the probability that A is true and B is true together? That's what we get from Bayes' theorem. Or this numerator can also be equivalently expressed as the probability that A is true multiplied by the probability that B is true given that A is true. So these are just equivalent ways here. And that's what we want to find here, the probability that A is true given that C is true. So we have all these 8 outcomes over here. So we want to focus on when C, given that C is true, given that C is true. That's what we are wanting to see, given that C is true. So that means that we're going to remove the points where C is false. So that's why here, if we want to look at where C is true, essentially we're trying to look at the regions where C is true. Given that, what's the probability that A will be true? So we look at all these 8 outcomes here, and we just want to begin looking for where C is true. So that's going to be in this region here where C is true, and not these other parts here. So we're just going to cross out these outcomes here where basically C is false. So we see here that we want, given that C is true, which is actually this is the color, given that C is true, and the given part is given here, given that this is the case, then what we'll do is we're just going to remove the parts where C is false, and then just focus on that part of the Venn diagram here, and then try to see what is the probability. What we're going to look for is what is the probability that out of this slice here that C And when C is true, what's the probability that A will be true? So we're going to look out of the slice of C, what's the probability that A is true? But we got rid of everything where C is false. So we can just hone in on the outcomes where C is true. And next we'll talk about how we can use Bayes' theorem here to help us out. So we want to find the probability basically that A is true given that C is true. So basically what we see here is that we are looking at C being true here, this green area, and we're limiting our scope down to just C being true. So what is the probability that A is true, of having A being true? A is given by this part here. But now that we know that C is true and all of these outcomes, we know that C is true. So that means that we have restricted everything to here, where C is true. And the sum is 0 plus 0.3 plus 0.2 plus 0.2. So this is, just 0.7 probability, 70% chance that C is true. So what is the probability that out of this, if we're here, that A is also true? So then we look at the intersection between A and see that, pun intended, that now if C is true, then A is true is this yellow part here. And that's the equivalent of us looking where C is true here and then seeing when is A true. So these two are the rows, 0.2 and 0.2. So this is this part here is 0.4. That's what we see, 0.4, that A is true. And then the chance that C is true is 0.7. That is a probability that C is true. If we add up all these probabilities, that will be 0.7. So out of the 70% chance that C is true, 40% of those outcomes have A being true as well. So basically, based on Bayes' theorem, what we can see is that the probability that A is true given that C is true here, so this is what this means, given that part, we're just saying the given that part is just this part here. So given that C is true, the probability that A is true given that C is true is just PA equals true and C equals true divided by the probability that C is true. So when C is true, one of all those outcomes when C is true, what part of it is A true? That's what the numerator is trying to say. What's the probability that A is true and C can both be true? And then what's the total probability that C is true? That's what the denominator is. So then please note that we can find the probability that C is true by just adding up these values. So whenever C is true from the joint probability distribution, that is just given by 0 plus 0.3 plus 0.2 plus 0.2, like we just add that up and then we get 0.7. So the probability that C is true here is going to be 0.7. So that's what we get. So this 0.7 will be the denominator here in Bayes' theorem. So if we note that this is the probability value that we're having that C is true, that's what we will put in here. So we're just going to put in 0.7 for the probability that C is true. Yay, we got it, Yaki. So what we want to find now is what the probability that A equals true and C equals true will be. But we already know that the denominator now for PC equals true will be 0.7. So that's what we added in. So the 0.7 given by adding up all these probabilities that C is true, adding this up is gave us our 0.7 here. So next, what we're going to do, and Yangshi says hi, we're on to the next step. We want to finish this calculation for the probability that A is true given that C is true. So we calculated the probability that C is true, which was 70% by adding this all up together. So next what we want to do is we want to find the probability that A is true and C is true. So that will involve us calculating, what is this? Sorry, but you get the idea. This is sort of what this is. That's what we're going to try to calculate. So basically, we're just trying to find the probability that A is true and C is true. So that's what this region here is. Hello, guys. So this region here is actually the overlap between A and C. And what you can see is that this pink part here is when A and C are true, but it's outside of when B is true, so B is false. But then this region here is when all three of them are true. And little guys, very cute. So basically, what you want to see is that when we're trying to calculate out of all of these where C is true, we notice that these two scenarios when A is true. So A is true, but B is false, and C is true. And A is true, and B is true, and C is true. So what we're going to see, and so this part here is the, just to map it, when all three of them are true, that's what this part represents, when all three of them are true here. And then the other one, the purpley one, sort of is this one. So we're just going to see the scenarios when A is true and C is true. It doesn't really matter what B is, if B is true or false. We just care about this overlap. Aww, between A and C. Oh, I want some attention. So basically, we just use both options for B here, true and false, since we're not concerned about the value of B here. So all we do is we look for when probability that A is true and B is false and C is true, plus the probability A is true and B is true and C is true. So you notice that we consider both options of B, false and true here. The important thing that we're looking for here, the important thing is that A is true. Oh, wait, let me just make that in yellow. Is that A is true and C is true, and then A is true and C is true. So then what we do is, all we do is we just map these probabilities here. We take this 0.2 when A is true, B is false, and C is true, and that's what this equals. This value just comes up here, and then the other value here just comes up here. So all we get is we just get 0.2 from here plus 0.2, so that's 0.4. So that's just, you can visually see it in the Venn diagram. That's why I've included both for both the three types of learners. So that's why this area in common between A and C is 0.2 plus 0.2, so it's 0.4. So please don't let that trip you up, that we have multiple variables here like B. Sweetheart. So the probability does that A is true and C is true is 0.4. So you can ignore all other variables. If you have multiple variables, beyond, 3, if you have 4 or 5, 6, the only thing you have to care about is just this variable A and C. And you can vary across all the values of A and all the values of B, because B is not important here. You're just looking for A being true and C being true. So what we see from here is that the probability that C is true, this is 70% here. That's what this is here. And then the probability that A is true out of this subset is just going to be 40%. We just added these two probabilities together to then get our 40% here. So that's the probability that A is true and C is true here. This part is what we focused on for the overlap. So when C is true, then there's a 40% chance that A will be true as well, that C and A are true. It doesn't matter if B is true. If B is true, that's the 20% here, this bottom 20%. But if B is false, then this is the 20% up here. So it doesn't matter, but this is what the 70% is. So we just have to plug in these values here. And so we basically, for the probability A is true and C is true, we just plug in 40% here. And then for the probability that C is true, we just plug in 70% or 0.7. And then this just equals 40 over 70, which is just equal to 57.14%. Please note that the probability that A is true, given that C is true, that will be 57.14%. So that's the probability that we will fall in this region here, given that C is true, in the yellow region where A is true, given that C is true. So it's 57.14%, which is kind of higher than the 40% chance that A is true by itself. Please note that in the second example, we are going to calculate the conditional probability using Bayes' rule to find the probability that A is true given that B is true. That is, what is the probability that A is true given that B is true? So growing up, my brother used to like Inspector Gadget. Da, 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 Inspector Gadget. Da, 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 da. So okay, so you can imagine that I saw the movie probably 1,000 times, Yankee. So what we will do is, out of this whole sample space, where all the probabilities inside this square or rectangle, the sample space usually written by is usually written as omega. Out of this whole sample space, we're just going to focus on B being true, on this area here. So Inspector Gadget is just going to limit the scope down to when B is true in this case, because we want to find the probability that A is true given that B is true. So we look at our joint probability table, and we're going to focus only where and only on the cases where B is true. Like this one, for instance, and this one, B is true. On all these outcomes, B is true, A is false, and C is true here. And there are all these outcomes here. A is false, B is true, C is false, A is true, B is true, C is false as well. So then what you see here is that we just essentially have been focused on the regions where this is true here. So that's all. We're cutting out the areas where it's false. So we see true, 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 false, for false, true, false, true, 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 false, true, true. So just whatever B is true. And this just brings us down to these four situations here, which you see are the 0.3, the 0.2, and the 0 and 0 here. So this is our sample space. So thus, what we can see here, and this cute little guy is also going to learn some statistics, is the probability that A is true given that B is true. So what we were doing is we were first looking at, okay, B is true. So let's just condition on B being true. And that's what we did over here in this Venn diagram. We look for where B is true. Then the next thing that we did is we sort of condition that, okay, out of this whole sample space, when is A true? So then we just focused on this region here. Okay, hi little guy, make it more comfortable there. So then basically we said, okay, well, if B is true, what's the probability that A is true here? So that's what led us ultimately to just looking here out of when A is true, no, B is true, what is the probability that A is true here? So we just focus on this slice over here. So again, that's sort of like looking at this table here. You can see all the values, but we're looking at when B is true, which adds up to 50% here. This is 50%. Then the probability that A is also true regardless of what the outcome is for C. So A can be true and B can be true and C can be true as well, or A can be true, B can be true, and C can be false. So when we look at the cases here, when A is true, we actually find that it's just going to be this 20% here, plus this 20% as well, which is going to be 40%. So that is what we see here is we're going to look when B is true here. This adds up to 50% here. This part here is 50%. And then we're going to look when A is also true there. That part, oh gosh, that part is going to be. So basically, what Yangshi is also going to learn is that this part, when B is true, is 50%. So that's the probability here that B is true. That is given by 50%. And what we will see here, that's this, if we add this all up, this is also 50%. These correspond to these here. And then we're going to look at when A is true, regardless of what C is. C can be true or false. It doesn't matter. So we can look at A being true, B being true, and C being true, or A being true, B being true, and C being false. And then we can just add those up. And what we're going to observe is that when we take this probability plus this probability here, this one, then we're going to observe that this just becomes equal to 0.2 plus 0, which is just 0.2. So that's what this is. This is actually just the same thing as, oh gosh, this is just the same thing as 20%. So if we see this, so what you're going to notice here is that this is this probability of A and B. So in Bayes' rule, probability A is true given B is true is the probability A is true and B is true, this overlapping part, divided by the probability that B is true. And so that is just, as you can see here, this giant circle of B being true here, this circle here, is the denominator, which is equal to 50%. And the numerator, that is just this intersection. It's when A is true, given that B is true. So in that whole sample space, Yangshi, in the whole sample space, we just want to find this overlap. We just want to find this overlap when A and B are true out of this intersection. So that's going to be 20%. So this is the point 2 plus this is 0 here. So this is 20%, which is what this is over here, which is also the same thing as this part plus this part here, the 0 plus this. And then the denominator is just going to be the 50% here. So 20% over 50%. And that's indeed what we observe here, the 0.2 plus this 0 here. The 0.2 plus this part here is going to be 0.2 here. And then the denominator is just going to be 0.3 plus 0.2 plus 0 plus 0, which is just 0.5. So this is just going to be 40%. So in Bayes' rule, what is important for you to understand is that the denominator, which is PB here, is always going to be greater than or equal to the numerator, because the denominator sort of sets the sample space. So PB, probability of B happening. So given that B is true, out of all the universe of outcomes when B is true, what's the probability that A can also be true? So you want to see when both of them are true, divided by the probability that this first outcome can be true in the first place. And if that outcome is true, then how likely is it? So if B is true, how likely is it for A and B to both be true? That's what this is showing you over here. So that's why here you look at the probability of B, and that's this whole space here with a bigger probability than what we're looking at here. A and B is restricting what B is down to what is shared between B and A. So that's why this thing is going to be less than or equal to the denominator. Or maybe they don't even share anything at all, and that's why this can be 0. If the probability of A and B is nothing, if they don't have anything in common, that could be 0. Or if they're just the same thing pretty much, then it can be 1. But in general, the denominator is always going to be bigger than or equal to the numerator, because the numerator is just a subset. The numerator is just saying, hey, I know that this outcome B has happened. So given that this has happened, can this other outcome also happen when B happens? So it's like being more restrictive that way. So to sum it up, basically what we did is we just look at the probability that B is true in this table. So we just subset it down to when B is true. And that's what we also looked at here. It's so cute. We also looked at that here in the Venn diagram. So in the Venn diagram, we just focused on B being true here. And then when B is true, then what's the probability that A is also true? So what's the probability then that A will be also true? So that's what we looked at here. So basically we derived that the probability that B is true, this probability here, is 50%. That's what this point here is. This is 50%. And then the probability that A and B are both true is just 20%. So we just have to plug them into this formula here. And then we have our 20% here, which is what this is here. The probability that this point here, which is what this is here, which is just given by this, and then the whole thing is green, and then this green part is given here, and that's what this part here is. And that's what we get here. So basically you just have to plug in this 20% divided by the 50%, and then we'll get the probability that A is true given that B is true will be just. So basically after you plug in those values, you're going to get 40%. So basically after you plug in, those values, you're going to get the probability that A is true given that B is true will just be 40%. So that's the probability that this will happen here. And so that's pretty good, I would say. So this is just the second example of Bayes' rule. So the probability A is true given that B is true is just 40% here. So Yangshi, as we can see here, this conditional probability that A is true given that B is true, it's 40%. So when A is true, given that B is true, that will be 40% here. So on behalf of Yangshi and me, thank you for watching this video on Bayes' rule. And please subscribe to our channel for more updates. Thank you so much for your support.